So good afternoon and welcome to this EURADOS webinar on pulse radiation fields, method of production and those measurements. I'm Marco Silari, I'm formerly CERN, now I'm a visiting scientist at CERN and in contact with the Polytechnic of Milano. I'm your host this afternoon. I will keep the introduction very, very brief because we have 4 speakers. You have seen the content of the webinar, you've seen the short abstract about the talks and the bio of the scientist going to give these 4 lectures, so I'm not going to spend time on that. I would just say a few words about EURADOS for those of you who are not too familiar. So EURADOS is a network of 85 essentially European institutions that involve more than 650 scientists. And EURADOS is performing research work in radiation dosimetry via a number of working groups. So the working groups perform research work, but there is a number of other activities which are actually managed by EURADOS, like symposia, workshop, winter school, annual meetings, intercomparison, training courses, and also webinars. So we typically have 1 webinar per year per working group. And this is in the framework of Working Group 11, who is actually led by Marco Caresana of Polytechnic of Milano, who is also one of the speakers, he's the first speaker of today. Working Group 11 essentially deals with high-energy radiation fields, both around particle accelerator and cosmic radiation in space. And actually, the motivation is to increase the knowledge and the expertise in characterizing this field and the associated dose. And for this, we run various activities, including intercomparison. So the webinar is actually split in 2 parts, exceptional, because normally we only have 1 webinar. We have 2, one today, one on Wednesday at 10 o'clock in the morning. Today, we're going to have 4 lectures on the method of production of those measurements. On Wednesday morning, Marco Budowski, my colleague, will actually host the second webinar on the methodology for measurements. So I'm not going to waste more time, and I'm going to give the floor to Marco Caresana, who will actually give an introduction on what it is pulse radiation fields. Marco, the floor is yours.
Thanks, Marco, for the kind introduction. I'm going to share my screen for my presentation. Hope you can see the presentation. Can
yeah, all good, good, Marco. We see it.
Okay. So in my introduction, this introduction talk is a general review on which are the characteristics of the pulsed and mixed radiation field, typically mixed because well, I will focus mainly on the pulse neutron field, but in any case, these are mixed neutron and gamma field, typically what is generated. So we have to cope with this characteristic. So I will try to say something about what is the problem, what is the definition of pulse field, and then eventually a focus on the neutron pulse field, simply because the Working Group 11 gathered most of its experience on neutron pulse field. Actually, the problem is known since a long time. This is a screenshot from a paper published in 1948, and all those time, it was pretty clear that the outstanding trends of huge machine and huge and complex machine accelerating charged particle actually could deliver the emission of particle in bars. And so the problem was first faced, well, in this paper. I guess this is the first paper who introduced this problem. There is also the EURADOS Research Strategic Agenda, in which the problem of pulse field is clearly addressed. So it is recognized actually this is a hot topic in research because we are still lacking of instrumentation which is explicitly designed to face the pulse radiation field. But what are the typical duration when we say pulsed? What we exactly mean? Well, this is in this slide you can see an overview of all the facilities that will be described later. But in general, the duration of the burst can be really variable. We can go down to just one moment that I use the laser. We can go down to picosecond or even lower for laser-driven protons, lower with laser-driven electrons. We have in the range of the femtosecond. But we can also get pulses of duration in the range of a few microseconds. So it is important to try to understand what is actually pulsed. Is 5 femtosecond or it is 10 microseconds. And there are a lot of facilities for testing material, for synchrocyclotron for proton therapy or spallation sources, but even conventional radiation therapy, the medical linac, actually deliver those in bursts. Or, of course, particle accelerator, but in the future, also the fusion facilities will have this characteristic. So, about the definition, if we have a steady field, it is pretty clear that the dose rate is constant over the time. In case of pulse field, we have a period of beam on, which can have a certain duration, and a period of beam off. So we can introduce the duty factor, which is the fraction of time in which the beam is on, and of course the duration of the burst. So both these two characteristics, so the duty factor and the duration, will have an impact on what we can understand, can define as pulsed. So a bit of nomenclature, because sometimes could be a bit misleading. When typically, okay, it is common to indicate the pulse field, but with the word pulse, typically we can indicate also the output signal from the counting electronics. So we can reserve the name pulse to this kind of characteristics. So the impulse coming from the interaction of the particle in the detector. And use the word burst to indicate actually the radiation pulse coming from the acceleration. So we have the burst duration, which is the time on here. We can have the burst dose, which is actually intended in quantities that can be sievert, gray, or other suitable quantities. It's not important what is the specific quantity, but is the total dose delivered during the burst. Of course, dividing the burst intensity or the burst dose by the time duration, we can have the burst dose rate. So the dose rate which is limited during the time on period. And then eventually we have the repetition rate, which is the number of bursts we have every second. When focusing on the pulse neutron field, Well, typically, a huge and important family of Newton detector are based on Newton or Newton's moderation using light Z material, like for instance polyethylene. So, if we look at the process, we can identify a thermalization time, which is the time needed for having several interactions, as in this case, several interactions to slow down the Newton energy to the thermal energy. And then eventually the thermal detector can drift through the moderator until it finds its way to the inner thermonewton detector. So we can split the moderation time in two components, which is one, the thermalization time, which is very, very fast. We are in the range of nanoseconds. And then a drift time, which is longer. Typically, we are in the range of tens or even 100 microseconds. And the drift time actually depends on the dimension of the moderators. So if we have a Born sphere set in which we have moderators of different sizes, of course, the drift time will change. And will change also based on the original energy of neutrons. This is an example. This is the thermalization position, so the point in which is reached by the neutrons where it thermalizes. And you can see that if I start from an original energy pretty low, 100 keV, the thermalization point is in this portion. Increasing the energy, I have a distribution of the thermalization position which is wider, and increasing again can encompass the whole moderator. Keeping this idea in mind, it is possible to define the time distribution, the time of arrival of neutrons to the inner detectors. And this time distribution can be very well approximated by a decreasing exponential. The blue point are evaluated with Monte Carlo simulation, and the red line is simply an interpolation with the decreasing exponential. This decreasing exponential is, of course, characterized by a decay time, tau, a typical time we call tau, which is in the range of 100 of microseconds, and can be different, typically can be higher for low, the lower is the neutron energy, and increases when increasing the dimension of the moderator. So for instance here, 1 MeV neutrons and 10 inches of moderation sphere, we have a tau of 124 microseconds. On the other extreme, with the same energy, an 8-inch has definitely a lower moderation time. This is for several spheres, which is the tau evaluated with Monte Carlo simulation at 1 MeV and 10 MeV. So it is clear that small spheres actually exhibit a very low, can change also 1 order of magnitude, the tau, changing the dimension of the sphere. So we can use this consideration to define what is a pulse field, and highlight that the definition of pulsed is defined by the specific instrument. If we take a towel, an average towel, let's say around 90 microseconds, we can identify with the red line the burst of radiation, which can last, doesn't matter if it is in the range of femtosecond, picosecond, nanosecond, or even a few microseconds. What dominates the characteristic time of the detector is the thermalization time. So that means that a pulse field can be defined like that if the duration of the burst is much lower than tau. So the duration of 2, 3, 4 microseconds actually is pulsed. But this is not the end of the story, because also the repetition rate plays a role. Let's imagine in this slide to have a repetition rate of 10 kilohertz. So we have one burst in this position and the second burst after 100 microseconds. So this burst has its own decreasing exponential with a specific tau. This second burst has also its own decreasing exponential. But if I sum point to point, I get a distribution of time of arrival of Newton's linear detector, which has this sinusoidal shape. So I generate a kind of ripple in the time of arrival, which clearly tends to be a steady field if I increase the repetition rate. Or, on the other hand, if I reduce the repetition rate, this ripple goes to a situation in which the specific burst can be very easily separated. So also the repetition rate actually plays a key role in the definition of what is pulsed. There is another important consequence of the thermalization and drift time, which is can be exploited to distinguish in between gamma and neutrons in a situation in which both neutrons and gamma are pulsed. This is an example for a specific kind of REM counter in this case, which is this is the Lupin, so the REM counter, which is specifically projected for coping pulse neutron field, in which I have an incoming signal composed by neutrons and gamma particles. So what I have as a current output signal of the Lupin is a very huge signal generated by the interaction of gamma rays inside the proportional counter. Of course, also gamma rays generate charge. And this signal is followed by the neutron signal after a time which is depending on the thermalization and drift time. So it is even possible to use this time difference to make a separation in between the neutron and gamma component. So as a final remark, we can say that pulse field typically encounters or sphere suffer of the time losses. Just to have a rough idea, for burst with a burst intensity around 10 nanosievert, sorry, I can have some important loss in an encounter. For defining a pulse field, we have to consider the comparison in between the thermalization and drift time. Then the gamma discrimination can be done on a time basis, as seen before, because it is quite different, the time of arrival of the gamma signal and the neutron signal. And probably the most important remark that I can add is that at present there is no reference facility for pulsed neutrons. So it should be needed, according to my opinion, but this is also an opinion shared by the Working Group 11, or the EURADOS Working Group 11. There should be some methodological effort for filling this gap, because actually the vast majority of measurement of neutron measurement occurs in a pulse field. The steady field is less frequent. We have steady field for environmental neutron dosimetry or on board aircraft, for instance, or we can have around nuclear power plants. But it is quite difficult to have steady neutron fields in acceleration facilities. And that's, I thank you for your kind attention.
Thank you, Marco.
So I can leave you back the floor, Marco.
Yes. We won't have question at the end of each talk. We will have a question answer session at the end, about 10-15 minutes. So I'd like now to give the floor to Veronica from Eli Beamlines, who will talk about the laser-driven accelerators.
Okay, good afternoon, ladies and gentlemen. I would like to introduce to the laser-driven accelerators, which can act nowadays as lasers can act as accelerators thanks to the discovery of short pulse amplification, for which Gerard Mourou and Jonas Strickland got their Nobel Prize in 2018. And the fact that this field in physics is being appreciated and looked very much into is confirmed as well by the second Nobel Prize in a few years after that, in 2023, to these people who got it for the methods for generation attosecond pulses of light for the study of electron dynamics in matter. So the lasers and hyper lasers are in focus nowadays. How the high power lasers are characterized. You've seen a similar picture in Marco's presentation. The one key parameter is the length of the pulse, which can be as low as few tens or even few femtoseconds or even attoseconds in some installations. Then what we are interested in is the pulse energy, the energy which is in one pulse. And when you make the ratio of these two, you get the peak power in watts. And thanks to the very short pulse, the peak power can be extreme. It can be ranging into petawatt region. However, the average power is quite low because the strongest systems nowadays still operate in the single shot regime or with a repetition rate of maybe 1 per minute, 1 per hour. So the average power is actually quite low. I don't want to go into physics of laser acceleration, just to mention some very basics. So when we are talking about acceleration of electrons, the method which is used the most often is the so-called laser wakefield acceleration, where the laser pulse which propagates through the plasma produces a wave behind which the electrons are accelerated. Is the similar principle as when you go surfing. So the same principle is used here. And then during the fast acceleration or deceleration of electrons, the X-ray radiation can be produced and is actually used as well. I've got here this short video, which I guess I have to look like this. This is a simulation from particle in a cell code, showing the electromagnetic field in red and green, electrons in blue, and in yellow you will see now the photons. The electrons accelerated from a thin foil are irradiated by the ultra-intense laser pulse. They emit energetic photons in the gamma region, and the pulse rips electrons out of the initially stored target into the free space in front of it. And then the fast electrons interact with the strong electromagnetic field, producing energetic photons. For ion acceleration, these are the methods which are being used, listed on this slide. The most common one is the target normal sheets acceleration, where protons are accelerated from the rear surface of the target by a hot electron cloud. And then after the hot electrons leave the rear side, they are attracted back into the target by the positive charge, which is left in the target. And electron sheets is formed at the rear surface, and then positively charged particles are accelerated by these sheets in the target normal direction. Again, this is the simulation in the particle in cell code. It's just 2D. It shows the interaction of a laser with a micrometer thick flat plastic target. You can see protons in pink, which for these particle simulations are reaching energy up to 150 mega electron volts per nucleon. And then in green, there are ions, carbon ions, which can reach up to 40 MeV per nucleon. All right, so where you can find this kind of installations. I've divided these into three big groups, into large scientific installations, into small university type labs, and into industrial installations. For the scientific installations, this is the map created by the Committee on Ultra High Intensity Lasers. This map is coming from 2020, when there were about 100 installations all over the world. You can see that when the first count was done in 2009, it was just 40. The peak power of these installations is about above 10 terawatts, or these installations are capable of producing light focusable to an intensity above 10 to 19 watt per centimeter square. How many installations there are nowadays? I don't really know. Don't know. The society is not giving the exact number. However, as we speak, this installation in United Kingdom is about to start installation operation. They started construction in 2020, and they expect to start operation this year. And another one which started to be constructed in 2024. It's in this very nice phase of construction. This is very recent photo from their webpage, just from last week. This is located and operated by Colorado State University in USA. In Europe, there is a huge infrastructure called the Extreme Light Infrastructure, which started its implementation in 2011, hosted the first users in 2018, and nowadays opens 2 regular calls for users twice per year. Its members are Czech Republic, Hungary, Italy, Bulgaria, and Lithuania, and there are 4 official observers. This infrastructure operates 3 sites. One in Hungary, which is focused on attosecond measurement techniques. Another one in Romania, which is focused on photonuclear physics. And the last one, Eli Beamlines, where I'm coming from, which is focused on production of secondary sources for various applications, for example, for medical imaging and radiotherapy. We are operating these 4 main laser systems. The most powerful one is the L4 Aton, which should be reaching up to 10 petawatt. And this system, this largest one, is now in its commissioning, should start shooting this year. The other 3 are in operation. What are the maximum parameters achieved by these systems? So the world record in terms of proton acceleration is about 110 MeV, achieved at Draco in Germany in a single shot regime. And for electrons, it's about 10 GeV, achieved at Bella, at TPV, both locations are in the United States, again in a single shot regime. At Eli beamlines, currently we have a beamline which is capable of operating at 3.3 Hertz and producing about 40 MeV protons. And for electrons, up to 5 GeV, again at 3.3 Hertz. Our targets are higher, but we are not there yet. The main difference between the world records and our situation is really the repetition rate. Then we have small university type labs, as I'm calling them. The thing is that nowadays, even the small commercial systems, tabletop size, can produce X-rays and accelerate electrons up to tens, 100 MeV of 100 of MeVs. Therefore, really acting as regular accelerator. And the number of these installations is increasing all the time because they are reasonably accessible. The issue there is that these laboratories used to be a standard laser science lab, and therefore the knowledge of radio protection is very basic there and very limited. Typically, there is no shielding in these laboratories, which causes issues as well. The last part where the lasers are being used on a regular basis and producing radiation are installations in industry where the plasma intensity is quite low, only 10 to 13, 14 watt per centimeter square. So what they produce is actually just low energy X-rays. However, they are operating on very high repetition rate. It can be hundreds of megahertz. And therefore, the cumulative dose can reach 10 millisieverts per hour, which is naturally an issue because the dose rate is really huge. The first country to implement some measures into their legislation is Germany. It was driven by PTV. You can find more information on the provided link or in the publications which are highlighted on this slide. These are the first works done by the German specialists coming from 2018 and 19. And there is one recent paper which is at this moment on the archive only. So what are the challenges of the field? I think you can maybe guess some of them by now. And the first of them is the shielding of these installations, because quite often the high-power lasers are installed into the existing laser facilities, which means that the civil structure, the building, doesn't provide adequate shielding. And the upgrades of the shielding are often difficult to be done because you have to basically rebuild the existing structures. Another challenge, which is valid even for new installation, is that the systems require many large openings for various services, especially for the laser beam, which has to basically go through. It's quite big for transport, and you can't juggle it too much because at each elbow you need to put a special mirror, which is quite expensive and affects negatively the beam quality as well. And then because the source and the description of radiation is a matter of research as well, and may significantly differ from expectations, you need the beam stoppers quite versatile as well. They need to be variable to be able to adjust to increasing knowledge of the field and various experiments. I've mentioned the source then, the field, the description of the ionizing radiation produced. So this is very, very pulsed. The length of the primary pulse can be 10 to minus 14 of a second. The repetition rate is quite low very often, especially with the strongest systems. from single shot up to 1 kilohertz. With the industrial system, it can go up to megahertz. What is being produced, it's mixed field with very wide spread of energies, from very low ones up to GeVs. And given the time structure, the extremely short pulse, the high dose rate in a single pulse can be really huge. As well, especially with the solid targets, you create a very strong magnetic field ranging hundreds of kilovolts per meter. This source stem is not well known and strongly depends on the experiment. So what kind of detectors we need? We need detectors which would have reliable response in pulse mixed fields for wide range of energies. Such detectors which would be able to detect pulses as short as some femtoseconds. Detectors which would not be susceptible to saturation in high dose rate environment, that will be resistant to electromagnetic pulses. But as well, we need such detectors that would be sensitive to that enough to detect small fractions of the EV limits. That will be available to provide online data, so we can actually follow the situation. And it was mentioned by Marco already, there is real lack of standardization of possibility to trace the measurements to some methodology standards. So this is a huge subject of research for all of us as well. So this is a brief overview from my side. Thank you for your attention, and you are welcome to post your questions in the chat.
Thank you, Veronica. Thank you for the wish list you gave us at the end, so that will hopefully be answered on Wednesday. We'll have talks about the detectors. So as Veronica said, if you have a question, you can write in the chat, and we're gonna address them at the end of the 4 talks. So the next speaker is Albrecht from DESY Hamburg, who will talk about the European XFEL. Albrecht, floor is yours. We don't hear you, Albert.
Yeah, now can you hear me?
That's
can
okay.
You hear me?
Fine.
Can
Yes.
you hear me?
Good.
And
All
see
good.
you, do you see my mouse?
Yes, we do see it. We see the slides.
Oh, thank you. So I'm Albrecht Leuschner from Deutsches Elektronensynchrotron. I would like to give a talk on measuring pulsed photon and neutron dose rates at the European XFEL. And of course, I want to start with the XFEL. So there are about 8 facilities around the world. There are 4 in Europe, in Hamburg, in Trieste, and in Villingen in Switzerland, and then 1 or 2 at SLAC in California, and 3 in Asia. And these are facilities that use a laser mechanism to accelerate or to produce very high brilliance X-rays. So our facility is 3.4 kilometers long in the city of Hamburg, and there are three sites here. Here the injector part, then 1.5 to 2 kilometers of accelerator, and then here some distribution shafts, and at the end the experimental stations. So here we show you a graph on the photon energy at the x-axis, on the peak brilliance and the y-axis. In this graphic, the DESY facilities flash, this laser facilities, and the European XFEL are compared with the 3rd generation synchrotron radiation sources, and they are orders of magnitudes higher brilliance. And this has the advantage that you you have a lot of brilliance to measure a single molecules to get the diffraction patterns for single molecules. But the disadvantage is that these molecules will be destroyed by the intense X-ray beams, and so cannot be used a second time. So the name of the game is you have to shoot as samples every 10 seconds or even faster into the beam, and then you get a signal of the detectors. So this is a nice picture of our accelerator. You see here, have here a photo of this 1.5 kilometer long acceleration modules. These modules are in principle freezers because the acceleration is done in superconducting niobium cavities, and they are operated at 2 Kelvin. So that's why these tanks have to be there. So, and here is a sketch of our facility. In the injector, the electrons bunches are formed and then accelerated through different stages of the accelerator up to 17 GeV, and then fed into magnetic structures that produce the X-rays. I would not like to explain all the numbers, but draw the attention to the electron beam energy. This is a GeV electron beam, and for our business of the pulsed radiation, it has a repetition rate of 10 Hertz. So how are these intense X-rays are produced? They are forced to fly in serpentines in these magnetic structures, and these electron bunches form then a slice structure, and this slice structure leads to this lasing process, and then produce these huge brilliances. So the X-ray that come out at the end of these accelerators and go into the experimental stations are in the range from 0.2 up to 25 keVs. And of course, they are pulsed. So here are some highlights of some titles of the experiments. Is material imaging and dynamics, high energy density science, which is important for the research of the process in planets in higher pressure, for instance, single particle and biomolecules, femtosecond X-ray experiments, small quantum systems, spectroscopy, and coherent scattering and soft X-ray board. So in the next slide, I will come to this FXE in a more detailed. So our samples are now in a liquid which goes here through the beams, and then chemical reactions is started by an optical laser pulse, which comes in red, and synchronized to this laser pulse is the XFL beam that probes the samples, and then you get the pictures from the detector, and then you can put together those pictures into a super slow motion molecular movie of the chemical reactions. So we can produce movie to a chemical reaction. So now let's come to our active dose rate meters at the XFEL. So it's in principle it's made out of 3 pieces. It's a simple plastic scintillator on top. It's designed to detect photons. Then here, this is a moderated helium-3 counter. It's a RAM counter type. It's designed to detect the neutron dose. And here, this is an electronic box. So now I would give you an example of what pulse radiation produces, what response is produced by pulse radiation. Here in the photon detection, it's an example of pileup. So I show you an energy spectrum. Here on the x-axis is the response energy of the scintillator, and the y-axis is the entries from 3 different radiative sources. You have the cobalt-60. This is the red curve, and the dotted lines are the Compton edge and the full energy. I gave only one energy of the 2. Then the cobalt at cesium 137. It's the green curve at 660 keV, and then americium 241 at 60 keV. And if you, as I would like to show you the pileup, then we have to extend the energy scale to higher energies up to, let's say, 1000 MeV. And that's why we have to change this number of entries per energy into the number of entries per the logarithm of energy, and then you get this lethargy representation, what is already known in the neutron spectroscopy. And now what I have shown here is the minimum ionism particle response limit. That means in this 4 centimeter wide scintillator, you can only deposit 8 MeV about due to this energy deposition. And this is for electrons, muons, and gammas. And now let's come to the response of this detector for pulse radiation. The scintillation detector delivers electrical pulses with a width of 20 nanoseconds. So it has a response duration of 20 nanoseconds. And for example, the photons with a burst duration of 1 microsecond, which is here, which comes from the gun RF, are registered individually. And you see here the spectrum on this graph. This is the energy, and this is the intensity. And then if you switch on the beam and the laser on the gun, and then switch on the beam, then we get 1 picosecond long pulses. And this 1 picosecond is much smaller than this 20 nanoseconds. So these photons coming from this 1 picosecond pile up to 1 higher energy. Here in this graph, we see a pileup of 30 pileups, and give this peak here, and with 100 pileups we come up here. So then let's come to the second example. What can we do with the response of the helium-3 counter and the moderator? So here the same business. We have this our time structure. We have a microsecond, the dark current, the picosecond pulses, and the repetition rate of 10 Hertz. And then the detector's time-resolved response is scanned for a burst trigger signature, and that marks the time 0, which is here. These are time spectra. And the following counts are binned in according to their arrival time, and the next trigger stops the sequence and starts a new one. On the right-hand side, you see this time spectra. These are two different time spectra and two different representations here. Here, the time goes from 0 to 10 milliseconds, and here from 0 to 100 milliseconds. And what we can see that this high charge means a high current, and means high intensity of the beam and of the radiation, and this is a lower intensity. And we see here three different signatures in this spectrum. This one, this is the integral response of this detector, which already Marco Caruana talked about, the Newton diffusion in the detector, and has here a time constant of 120 microseconds. This is here. And then you have another time constant here. This is the Newton diffusion in the vicinity of the detector, so floor, ceiling, and walls. Has a tau of 2 milliseconds. And you multiply this with the speed of thermal neutrons to get a size of 4.4 meter, which is our rooms. And then at the end, which is not really understood now, is you have a background of neutrons. So there is the natural background for neutrons is 10 to the minus 6. It's 1 order of magnitude lower than here. And we see here 2 orders of magnitude higher neutron backgrounds here in this constant region. And this gives us our assumption is that these are delayed neutrons come from decay of long-lived radionuclides that are produced by high-energy neutrons. So we have a kind of spectroscopy, high-energy neutrons here, low thermal neutrons here, and an integral spectral signal here. Okay, let me summarize my talk. So the time constants of the production of pulsed radiation are determined by the accelerator, so the repetition rate, or the burst duration from a gun, or from the RF. From the laser of the gun, and then any dark current. And this repetition, this time structure is repeated by every 100 milliseconds in our accelerator. And the detector properties describe how the pulsed radiation is reflected in its response. For instance, you get pile up when the burst duration is much smaller than the response duration. So if this 1 picosecond fits into this 20 nanoseconds, then it will pile up. And here, this the helium-3 proportion count is much slower because of the charge collection in this proportion encounter. And that's why you will get a pile up even in the 1 microsecond range here. So what I haven't talked about is, of course, you get some higher intensities than saturation that can be described at some extent to the half response dose. Okay, thank you.
Thank you, Albert, for the nice presentation. And now I'll give the floor to the last speaker of today, Alexander, who's going to talk on medical flash machines. Alexander, the floor is yours.
Hello, thank you, Marco. Can you see my mouse?
Yes, all good. We see the slides and the mouse.
Very good. The talk today is medical flash facilities, and the general topic of the seminar is pulsed radiation. So of course, irradiation here is pulsed, but I will start with a provocative question. Is cancer one of the most important problems to solve in the 21st century? And here you can see the proposed answers. You can tick your virtual box. In the next few slides, I will try to convince you in one way or another. The first argument would be with this warning prediction from the World Health Organization. On the left, you see the plot that for the next 30 years, the estimated number of cases, new cancer cases per year will grow. So this is the data for males and females separately. So roughly 70% increase on average is expected. And on the right, a similar plot, even more increase, 85%. But in this case, this is even more scary. This is the estimated number of annual deaths from cancer. But instead of looking in the future, maybe let's rewind 70 years back and look in the past. If you look for the statistics, again from WHO, for the last 70 years, it was about factor 4 increase in the cancer cases. When I showed the similar plot in the workshop in Mexico about a year ago, the reasonable remark I got was, what about population growth? What about life expectancy? This is probably dictating the number of cancer cases. And to answer on this, I'll show you a bit of more data. So this is the world population growth, roughly a bit more than factor 4. So indeed, population grows. And then the life expectancy also growing. And if we normalize the population growth on the life expectancy divided by 100 years, we can see that we nearly reach factor 6. Now the question is it outgrowing cancer cases? If you plot these two on one plot using two different axes on the left and right, this is not really clear to understand. Therefore, we will jump to the normalized plot. So on the left here, you see the annual cancer cases per 1,000 people. So we normalize it per capita pretty much. And in two cases. So on the blue plot, you see the number of cancer cases for the last 70 years normalized by population. And on the red, you can see also the weighting factor of the life expectancy. So if you look on the blue plot, it's clearly we can say that number of cancer cases outgrowing the population. And the trend is that it increases quite rapidly, I would say. If you look on the red plot, it's not that obvious, but still you can see the increasing trend. Now, if you look for the last 15 years, we can clearly see the increase, meaning that, yes, this is not just population growth, this is not just expectancy, life expectancy growth, this is more than this. So the cancer is an important problem. Now, if we, let's say, ignore this prediction, which I showed on one of the first slides, and we just take the data from 2020, and we do a simple math exercise. Let's imagine XYZ plans to live up to 100 years, and assuming this chance to get cancer and 100 years of life, there's a 25% chance that XYZ will have cancer during 100 years of lifetime, which is roughly double than 70 years ago, and this is 1 out of 4 people. If we say that it's only 50 years life expectancy, when 1 out of 8 people will most likely have cancer. They know that once a person acquires cancer, it's very complicated to treat it. Therefore, here's my answer, and I hope you will have this question in your head after this talk. And now let's talk about the treatment of cancer. So here's the diagram showing the major ways to treat cancer. And here I want to emphasize that radiotherapy stands out around 40%. And on the right plot, you can also see that many methods of cancer treatment actually applied and combined together. And yes, radiotherapy can be combined with chemo, with surgery, and so on. So in the following, we will just talk about the radiotherapy methods. We can split the radiation therapy methods by the carrier. Basically, what type of particles would deliver the radiation to the patient. And here I show you 4 groups in this classification. So the first one is photons. These are the most common machines, X-rays, gamma rays machine. The photon production is actually coming from electrons hitting a target of the material with a high Z number. And these machines accessible. They works nearly for all type of tumors if it's localized. And then they're relatively affordable. But the main disadvantage is, for example, there's no sharp dose deposition. The second category is almighty protons. Here's the example of one of the most compact proton machine. They work very well. They feature the Bragg peak, meaning that depending on the energy, the dose can be rapidly deposited at the tumor location. However, the main downside is it's very expensive and not enough facilities built. There are more patients to be treated than facilities available. And this statistics is for all countries, including countries like Switzerland or even United States. Literally, we are missing radiation facilities here. Now, if we talk about the older brother, the more powerful one of protons, it's heavy ions, even sharper Bragg peak, even stronger biological damage. Ultimately, very nice machine, but even more sophisticated and more expensive to build. As a result, hospitals cannot really afford it. And now the final category is electrons. On the right, you can see two examples of the commercial machines reaching energy of around 10 MeV. So these machines are cheap and easy to deal with. There is no Bragg peak, but this can be also used as an advantage. And then the only downside, if you ask the community with this machine, is, oh, they say, okay, you can only treat tumors on the surface like skin cancer because you need high energy to reach deep-seated tumors. But with the current technologies of the accelerators, this is really possible. Now, if we add to this table the possibility to generate ultra-high dose rate, for all the first three categories, it's really hard to reach ultra-high dose rate, especially if you're talking about the large field size. For electrons, however, it is possible to reach ultra-high dose rate, even delivering at the same time very large field size. Now, why UHDR is important? This is maybe a very boring slide without any pictures, but please take a look on this and read it very carefully. So first of all, conventional radiation assumes several minutes of treatment time. And if we reduce this window, there's a simple time budget where we can save on time of the treatment. So imagine the radiation is significantly reduced with all the dose delivered in split of a second, let's say below 100 milliseconds. It means you can have faster radiation, more patients. And then in addition, you have less organ fluctuations during the radiation time. You can really neglect this. And then at the end of the day, it's patient comfort because you can have treatment for shorter time interval. Now, the second and even more important reason is the miracle known in the field as the flash effect. There are two key ingredients for the flash effect. UHDR duration with under 100 milliseconds shows sparing of the healthy tissues in comparison with conventional irradiation. And the second, UHDR radiation in 100 millisecond time interval shows as efficient tumor control, meaning that damage to cancerous tissue is at least as effective as in the conventional radiation. So this is really a miracle because you can destroy the tumor and you can then spare the healthy tissues, and you can increase the dose to deliver more dose to the tumor and at the same time have, for example, less damage to the healthy tissue in comparison to the conventional radiotherapy. The first clinical irradiation in flash, not yet demonstrating the flash effect, but just irradiating in the UHDR mode, was in a hospital in Lausanne, CHUV. And here you can see the example. It was not the medical machine was used, but actually a prototype delivering 5.6 MeV electron beam to 75 years old patient. And this patient underwent several procedures before, and actually he was really cooperative with many different new methods. He really wanted for the field to be advanced, not only get cured himself. And here you can see the example that how his skin looked day 0 after the irradiation, and 3 weeks after radiation, and then 5 months after the radiation. And so this was the first clinical evidence, and then many experiments continued with biological samples, with some samples including cells of the tumors and healthy cells, and then of course experiments on mice. So the field actively worked on understanding the flash effect and then what would be the optimal condition for the flash effect. So if we summarize, what would be then an effective ingredients for the potential solution with electrons? So first of all, we need to reach deep-seated tumors, therefore we need energy of 100 MeV range roughly. Then this is possible due to high gradient acceleration technologies. And then we also want to deliver a lot of charge in a very short time interval, reaching the UHDR regime. And then on top of everything, of course, also medical doctors said we ideally want to have this machine not with a team of accelerator operators, but autonomous. So meaning it can basically be a turn button machine. And then we jump to the following slide, which is summarizing the established collaboration between CERN, CHUV Hospital in Lausanne, and the French company Terric, which joined the forces several years ago with an attempt to actually create first a design and then eventually a machine, the medical facility, which will be capable of producing VHE, UHDR radiation and treat patients. Here you can find more information on this news, and then this was our first vision how this machine will look like. Back in the days, we were no data suggesting that flash can work in time fractionation and also in spatial fractionation. Therefore, the goal was to actually have irradiation coming from different directions at the same time. So here you have a LINAC starting with photocathode, and this one is the X-band LINAC comprised of 8 X-band structures. And then you have a huge separator magnet dividing the beam depending on the energy on different trajectories, and then all of them will reach the patient with a large field size. The first CDR and TDR were produced, and then as soon as they were pretty much released and finished, we start thinking that maybe this machine is too bulky to be built, and at the same time we got some insights that maybe flash will work in fractionation. And therefore, the next design, which was decision was taken in late 2023, was to actually keep only one line. So this simplifies the facility significantly. And this was our, let's say, a working solution, starting with 1.3 meter S-band based photo injector, then with around 6 meter X-band LINAC, and then with beam delivery system to deliver the large spot size at the isocenter, as large as 20 centimeters. So then this design was worked on actively, and we published the technical design report, which is available on the CERN website last year. And we were about to actually start building this machine in the CHUV Hospital in Lausanne. But before I jump to this, I will shortly explain you a few key features of this machine. So there were several challenges. First of all, in terms of the uniformity of the radiation, in accelerator physics, we used to work a lot with Gaussian beams, but the doctors really want to have uniform beams. So this challenge was solved by introducing and enhancing the space charge dominated regime at the photocathode. And in this regime, which we showed first in simulations and then experimentally, beam from the Gaussian already at the photocathode can become uniform. And then if we do a proper beam dynamics for the machine, we can keep this uniform. Then, of course, there were many studies done to understand if whatever works in simulations will work experimentally by introducing sensitivity studies and stability studies, and all of these is comprised and explained in the TDR. And then if you look in the details how the uniform beam look like, so a bit of beauty of physics here. So the uniformity is reached in transverse plane, but if you look on this beam in 3D, and if you look inside of the beam, you actually will see the hollow beam. So what we call a bubble beam, meaning that because of the space charge forces, the particles are really pushed on that side. So this is like this. We wanted to treat cancer with bubbles in flash regime. So this is the summary of the key parameters. I do not want to go into many details here, especially that is so limited in time. I can only tell you that first, the radiation is really pulsed. So here we're talking about 500 individual bunches per train. Each bunch is about 1 picosecond short. Or here you can see the length of the bunch in the millimeters. The charge is about 200 picocoulomb, and then you have multiple trains like this. So, for example, 50 or 40 trains, depending on the final dose you want to deliver. So this is really the ultimate machine which we were about to build at CHUV. So here is the photographs of the CHUV bunker in the end of 2024. And the original plan was following: finish the TDR, start purchasing the component, finish the bunker by the end of 2025, and start installing 2026, meaning that now we probably would already have the first installation. But the reality was unfortunately a bit different. So when we finished despite finishing the TDR, we had a few obstacles. The first one was the budget freeze in CHUV Hospital, which actually paused down the project significantly. Also, at the same time, the commercial company decided to reconsider the complicated X-band design and look for some alternatives, because we need to understand we can make the very nice machine, but if the price tag would be too expensive, it cannot be affordable still for hospitals. And if we think about the cheapest proton machine, it's 25 million. The target for this machine would be, let's say, 10 million. Therefore, we have decided to take the opportunity to reconsider the design, and then basically all the cornerstones of the original design were reconsidered. So instead of photocathode, we looked at the thermionic gun. Instead of the X-band, we looked at the S-band design. And then even this idea of creating the uniform beams by space charge was rejected as a bit too complicated. And finally, the main goal was to use as much as possible off-the-shelf components. And with this, we came with, let's say, very simplified design, as simple as the scheme shown on this slide. And here is the beam parameters. You can see that we went from 200 picocoulomb to 20 picocoulomb bunches, increased tremendously the number of bunches here. And so this design is definitely ready to be built. And for now, how the situation looks like with this machine, we are TERIC, so TERIC, and still with some residual collaborations with CERN, is currently looking for investors. We have agreement with some hospitals in France, in particular with Gustave Roussy Hospital, to start installation in 2028. Meanwhile, we actively looking for alternatives where we can start installation maybe already next year, because situation with CHUV is still not clear. And the main reason for this is we think this field needs to be, so we think that this machine needs to come very soon. And of course, there are different groups actively working in this direction, but we think that the time is now to solve this problem, and the time is to do it with electrons and very high energy electron beams with UHDR mode. With this, I want to thank you for your attention. With this Hart from Clear facility, and I just jump to the very, very last slide, which showing you that, so this is the Clear facility at CERN, this is the radiation facility and the Clear team, and here we do a lot of experiments to actually understand flash mechanisms and to understand what would be the best parameters for the future medical flash facilities. Thank you very much.
Thank you, Alexander, for the nice talk. Thank you to all the speakers. I mean, we're only a few minutes over time with respect to what we planned, so I think we can take about 10 minutes for questions. The best would be that you type your question in the chat rather than raising your hand, because you have quite about 70 people joining today. So you can type your question in the chat, and either myself or Francesco can readdress the question. But maybe I can start with a quick question to Alexander, in fact. Now, one of the advantages you mentioned about of the flash is the treatment time versus the time for conventional treatment. I sort of partially agree, because it is true that, I mean, with flash, you treat in, a fraction of a second versus maybe 1 or 2 minutes. But there is a setup time that is unchanged, and that's pretty long. And I would say it's even more important in flash than with conventional, because you give one shot, so you cannot miss it.
Yeah, of course. Yes, I fully agree. Of course, there is a time where you need to switch the patients. But if you're talking about the future, how to optimize this, after we show the prototype is working, we can think about how we switch radiation from one machine to the different treatments room. And this can be done in, let's say, a split of the second. So if you increase the number of chairs where you can sit the patient, and if you can switch the radiation, then you can literally do this fast. But yes, I agree with you that, of course, the main beauty of flash is not just the shorter radiation time, but the fact that you can spare the
real spare. Yeah. I see no questions in the chat still, so maybe there are no questions.
No, looks like there is no question in the chat.
Yeah.
But are they allowed? Everyone is allowed to write in the chat? Is that?
I think so. I think so.
Yes, it is.
So on Wednesday at 10 o'clock, we will have the follow-up of this webinar, 3 lectures, and that would be on the method for for doing dosimetry around the pulse beams, because we've seen in some of the talks some hints already where the problems are, and this would be fully addressed in the 3 lectures on Wednesday. I still see no questions, so maybe, Francesco, I think we can maybe close it here. Everything very clear, I think. Well, we've got a bit, slightly longer.
Can I ask a question to Veronica, actually?
Of course you can.
Yeah, thank you very much. Yeah, so you mentioned that there is a question of the beam dump. So once you produce the high energy particles, you need to dump them. So I had this idea recently where I was like looking into how to optimize the beam dumps and so on, and then came to my mind, but why don't we consider deceleration once we shoot the target, and then we don't just dump everything in the beam dump? Why don't we add a bit of decelerator to the scheme? And I mean, it can be complicated. I'm not saying it's straightforward, but maybe this is the solution if you want to really avoid dumping high energy particles to the material. But what do you think about this? Is it possible with lasers?
I think that, at least in the experiments which we've run so far, it could be difficult in the sense that they are using the beams for various kinds of experimental activities. So they're actually using the beam, and then you have to do something in it. And this is already in the air. Might be worth looking into. I'm not saying no directly, but I think that in terms of the variability of the use, it's a bit complicated. So, I mean, the general issue which we are facing is the characteristics of the original source in terms of divergence, in terms of energy, in terms of pointing stability. So, I mean, the beam dump itself, in general, it's something which is well known. But the thing is that you have to build some structure which would accommodate a huge series of experiments and work for each of them and not be too big. So this is the issue. And quite often we are actually surprised. And not only us for radio protection and simulation, but the people who are running the experiments themselves. So there is lots of unknown still in this field of laser plasma acceleration.
Thank you.
I mean, Veronica, how do you do, I mean, individual dosimetry at your facility? Do you have actually anything that works for a personal dosimeter that would?
Well, I'm taking the easy way. So I'm kicking everyone out, meaning that I'm actually measuring or allowing people only in the areas where I can reasonably rely on the current method of measurements.
Okay.
So in that respect, I'm able to ensure radiation protection of the personnel. On the other hand, that doesn't reduce the issue as such, because we need to be able to understand and be able to measure even in this harsh environment for the future uses, especially for the ultra high dose therapy. Then you will have the patient and you want to irradiate the tumor only by the defined dose. You need to maybe measure person or someone accompanying the person, whatever. So my way is the easy one. I'm confident I'm able to do it. However, there is this huge field ahead of us. The same actually is valid for the small labs where you can't have such massive shielding as we are having. So yeah.
Okay. So there's a chat.
Yep.
The chat. There's a question for Alexander. Maybe I read it. So I would like to ask about the current prototypes of machine using flash radiotherapy. What types of accelerator systems are currently to be the most promising for clinical implementation? And regarding dosimetry, which detectors are mainly used nowadays in these flash prototypes to measure ultra high dose rates accurately? And what are the main dosimetric challenges encountered in present flash radiotherapy prototypes, especially concerning detector and saturation and dose rate dependence? Part of this question I think will be answered on Wednesday, but please, Alexander.
Yeah, there are a lot of very good questions. So thank you for this. So I will start with the first one. So the current prototypes machines. So we're at two directions. So the let's say the companies they have few prototypes of flash machines with low energy electrons, which is 10 MeV roughly. I showed few on the pictures of two companies. There are a few more on the market. And then there are, of course, irradiation facilities such as Clear and then other facilities in Germany and UK, which are capable to make the beam in literally the UHDR mode and also with very high energy. So this can be also considered as the prototypes, because at these facilities you can do experiments and actually understand a bit the mechanisms and the nature of the flash effect and find the most optimal regime. Now, if we talk about what types of accelerator systems are the most promising for clinical implementations, well, in my opinion, so of course I might be biased because I'm developing the system. I think if we talk about electrons, you will need to take the technology which is as simple as possible and as most robust as possible, because yes, you can try to save a bit of space by going to high gradient acceleration like X-band, but then at the end of the day, you will not save much because your machine will be too complicated, and then you will have to add more power so in the equation. And this is because what we're really trying to do here is we're trying to deliver a lot of charge in the very large field size. So it's really putting the loading of your power source, and you really need to have a lot of power. So if you even save the space of the LINAC, you need to think about the space of the classrooms, for example, as a rough power source. So that's why for me it's simply, if you want to go with electrons, just go with standard S-band, and then the technology which was a long time ago, and just build the machine literally. But yeah, of course, it's not that straightforward. Now, regarding dosimetry, which is a very good question in the sense that, yes, so if you go to UHDR radiation, and also if you go to, for example, low energy, the standard ionization chambers, they saturate very quickly, and therefore several groups working on a different type of detectors. There's flash diamond direction, there's direction which we use at Clear, where we use simply the charge density method, where we measure the charge distribution, and then so on the transverse screen monitor, on the YAG screen, for example, and this can be very non-invasive because you can have very thin YAG screen, for example, and then by charge density we can predict the dose very, very carefully. So this can be, in general, if you have fast screens, you can even do let's say the bunch-to-bunch measurements, so which do not exist so far. Let me see if I covered everything. Yeah, so yeah, I think pretty much all the questions. But feel free to just you know, follow up in the chat, or maybe even with a mic if you still have some questions unanswered.
There is a question from Fabio Pozzo from CERN to Veronica. Given the challenges in terms of measurement, simulation, reproducibility, how do you manage regulatory aspects and exchange with national regulatory authorities?
This is, Fabio, a very good question, of course.
Radiation protection physicist question.
Yeah, I mean, it's a new kind of installations, or in our case, the national authority is called State Office for Nuclear Safety, and they are really paying close attention to what we are doing. I have several meetings with them per year. Some of them like formal audit, majority of them informal discussions. And we are basically combining several methods to gain as good understanding as we can. Meaning that the employees, the ones who are really working with the sources regularly, they have the legal dosimeters, which are based on passive dosimetry. Used to be films up to the end of last year, and now nowadays the OSLs. And as well, they are having the electronic dosimeter, which of course is not too reliable in this field, but it's good for measuring the activation products. And behind the shielding, even the EPDs are not totally blind. Then we are having online monitoring system based on stationary detectors, and we are having passive monitoring for the environment as well. So all these combined are giving quite a good amount of information. So if there are some discrepancies, we can work with them. We can try to evaluate specific issues and improve the system. And as well, for ensuring that people actually cannot be inside the experimental halls when the radiation hazard is really huge. The entrance system is not just a safety system, but it's a safety certified based on international standards, ISO 608, I think, for functional safety. So it's something which is really confirmed or it's in line with the standards in industry and the big installations. So that's what we are doing.
Thank you. So I don't see other questions in the chat, so I think we can close the webinar here. I would like to thank all the speakers, the EURADOS team for ensuring the organization. The webinar has been recorded, so it will be posted on the EURADOS YouTube channel, and the slides will also be available on the EURADOS website. And I invite you back here on Wednesday morning at 10. There will be a follow-up webinar hosted by my colleague Markus Widowski on measurement techniques. Thank you very much.
Thank you.